Like, let's switch better. I think it's okay. Yeah. So, the last how we do so I can see you are the only one with the project. Okay, hello guys. So sorry, content bullshit and bullying. Let me confirm that you can see clearly and you can hear very clearly. My audio and my video is clear. Yeah, all right. Good evening. We can go on with our class now. And is the audio okay? Okay. All right. So we do not have the luxury of time. Throughout, we should be done with whatever we have to do here. So moving on, introduction. I was trying to illustrate the essence of difference to organic chemistry as we are just about 4 days or 5 days there about your jam mock exam, which is started of this month. So we're expecting all questions minimum in jam chemistry on organic chemistry and such. You shouldn't waste your chances of getting 5 full marks. If I told you you're going to have to miss any, well, you should miss zero questions. All right, so that's why we're going to be having this class to help you in your organic chemistry class. Brought to you by the Distinguished Scholars Academy. My name is Manuel, but you should call me Dr. J. Right, so we're going straight into the business. Uh, Organic chemistry. So I'll be working with this outline for the time being. Introduction to organic chemistry. Then we'll move down to the terminologies or terms that are relevant in the study of organic chemistry. And then we go down to petroleum, study aromatics, and ultimately we go down to nomenclature of organic compounds. All right, so that's what we have for tonight. So we start off, you see, introducing organic chemistry. At that time, you have your notes and take proper jottings where necessary. Although I may not be able to wait to give you notes, but of course, certainly, if you are smart enough, which I believe that every one of you can, you should be able to take down notes. Okay. I can see that it said it's a bit low. I'm not exactly sure what's wrong with YouTube, but definitely nothing wrong with the camera. So I don't know whatever is wrong with YouTube algorithm. Is it clear without movements? I think without movements. Let's see. Without movements. Without movements. There's a messages. Yeah, it's a bit low. Okay. What the hell? What the hell is wrong? But it's not low. It's very clear. Yeah, that's done. I put it off, turn it on again. What is wrong with the camera? Is it the camera on? It should be not. Oh, okay, it's wrong with you. So this is what I'm going to do. I think it's. I think it's clear now. Sorry, for it to. The network is a bit slow, so that's how this is transmission. All right, so I think we have a clear video now. We should go straight now. I mean, having a life in Nigeria is something very, very crazy that I don't think we can ever get to a point that is going to be efficient. But sometimes we need it, and we cannot continue to escape from it. So the earlier we begin to address it, the better it gets. All right, so we do not have the luxury of time, like I've said. Welcome to the session, and I believe that the audio is not a problem. Okay. You people have come because this is a lot of handwriting. Let's get used to our handwriting. All right, so all right, so I think we are good to go. Everything is clear, and the audio is also not breaking. So I'll move straight to business, introducing organic chemistry. So yeah, what are the things that you must know about organic chemistry? First, the first thing that comes to mind when it comes to organic chemistry is to understand that it is a branch of chemistry. Okay, that's the first thing. And I like to explain my topic before even going into it. So when we say organic chemistry, it has to do with a chemistry that studies organic. So we must first, of course, know what exactly do you mean by organic? What does the word organic mean? So you must have heard about stuff like organic soap and all of the likes of them. Those are stuff that you obtain from natural products like ashes and all those whatever skincare products that you guys spend money on. That's by the way. So when we say organic, organic has to do with substances that are obtained from natural products, substances obtained from living organisms, which we expect according to your biology to be plants and animals. So organic chemistry will deal with the branch of chemistry that studies all the components, constituent compounds, molecules, and all of that that we can get from living substances, which can be plants or animals. All right. So if we know that already, uh, you already have a good knowledge of what chemistry is. You say chemistry is properties, functions, and uses of matter. And from there, we study about the different branches of chemistry, like your physical chemistry, which studies all of the basic things that we see physically and how it applies to chemistry. When you talk about all the different concepts you study, like your atoms, under atomic structure, talk about your electrochemistry, you talk about your periodic table, your gas laws, and all of those fall under the category of what we call physical chemistry. Okay, we also have industrial chemistry that has to do with the application of raw materials to give us finished products. So that's all about industrial chemistry. We have inorganic chemistry that studies about elements that we have. For example, oxygen and its compound, hydrogen and its compound, carbon and its compound, and a whole lot of them. All those fall under the category of what we call inorganic chemistry. So, and the most important one that concerns us this evening, we move down to organic chemistry. All right. So for organic chemistry, like I said, it's a branch of chemistry. You want to know what organic means. That is substances that are obtained from living sources like your plants and animals. Now, if we leave that, we look at the chemical definition of organic chemistry. What does it exactly mean? So different aspects of chemistry, but if you look at that inorganic chemistry of a thing, the inorganic chemistry, we have oxygen, we have carbon, we have and the likes of them. But there is a special chemistry that is dedicated to carbon on its own. That's why if you look at your textbook, you observe that before you even get to the end of your textbook, there's a section that studies carbon and its compound, telling you that carbon has been separated from the general inorganic chemistry. You know, we have metals and non-metals at the end of your textbook. But carbon and its compound is about chapter 6 of your new school chemistry, telling you that it comes of very, very important, even before we go deep down into the major chemistry business. All right. So what exactly is the work of carbon, or how is it related to organic chemistry? There is no big deal. Without carbon, there cannot be organic chemistry. So we say that organic chemistry is the study of carbon containing compounds. Okay, I take that again, related to carbon. Okay, we do not have a particular chemistry. Maybe for oxygen, we would have called it oxochemistry or oxygen chemistry or something. But of course, the only one that is very much popular around is organic chemistry that studies carbon and its compounds. Now, it studies carbon alongside other elements like hydrogen, sulfur, oxygen. Not all compounds of carbon are oxygen. This is a rapid revision class. So, of course, I'll be a little bit faster with time. So, if organic chemistry is study of carbon containing compounds, we want to think about like carbon and hydrogen. CH4, that's methane. Is it an organic compound? Yes. You want to think about compounds like CH3COOH, that's ethanoic acid. Is it an organic compound? Of course. Now you think about compounds like CO3 2-, that's your carbonate. Are they organic compounds? Definitely no. So not all carbon containing compounds are organic compounds. So your carbonates are not organic compounds. That's one thing we should know. Of course, oxides of carbon are also not organic compounds. Think about CO2 and CO, your carbon 4 oxide and carbon 2 oxide. They are inorganic compounds. All right. So if we know that already, I think the next thing we should move down to now is to look at what exactly is there that makes carbon special. Because if We do not have a chemistry dedicated to oxygen. We do not have a chemistry dedicated to other things. Why exactly do we have a carbon chemistry? Okay, so the idea of organic chemistry started off with people thinking that you can only get compounds from naturally or living organisms or living things. Okay, so until 1827, 1828 thereabouts, a particular German scientist came up with a concept that proves the idea that everything organic compound must be from a living thing. Not every compound that is organic compound must come from a living thing. So prior to the discovery of that German scientist, whose name we are going to learn subsequently, everybody believed that if we are going to have a compound that's organic, it must be from a living thing. You cannot go to a laboratory and synthesize an organic compound. So that was in keeping with what we call the vital force theory. The vital force theory. Okay? The vital force theory. All right. So the vital force theory was explaining the fact that you can only get organic compounds from substances that have life. However, things have evolved since 1827, 1828, where the German scientist Frederick Wohler, okay, Frederick, depends on different spelling that you may come across, but I think this is my own version that resonates better with me. So Frederick Wohler in 1827, 1828, he disproved the idea that organic compounds must only agree with vital force theory. He said that we can actually get organic compounds from non-organic sources. What exactly or how did he do that? So he was able to synthesize an organic compound, urea. Okay, you know, urea is a compound in the formula CONH22. Okay, so Frederick Wohler was the first guy to synthesize this compound, urea, but he did not synthesize it from a plant or animal source, not from an organic source now, but from an inorganic source. He synthesized this compound from ammonium thiocyanate. Ammonium thiocyanate. Okay, that is NH4CNO. Okay, Frederick Wohler synthesized urea, CONH2, from ammonium thiocyanate, and that was a very breakthrough that led us to agree that the vital force theory is not a must. That is, we can actually synthesize organic compounds in the laboratory and from non-organic sources. Now, with that set in the foundation, we should move on to study why exactly do we have a chemistry that is dedicated to carbon. Carbon must definitely be a special kind of chemical element. So what are the properties that make carbon quite unique for us to have a whole branch of chemistry dedicated to it? That leads us to the next part, uniqueness of carbon. Uniqueness of carbon. So you must have rightly seen some of these things. There are certain properties that make carbon unique. Number one, carbon has tetracovalency. Carbon has tetracovalency. Now, what exactly do I mean by tetracovalency? Tetra means four. Covalently has to do with covalent bond, which is the sharing of electron. So carbon is number 6, 1s2, 2s2, 2p2. That's what we expect normally. But we know that elements are better stable when they are half filled or completely filled. So because of that, this S and P, they are in the same orbital. So we need to make sure that at least they are half filled. Okay, imagine that we have 2s2 and then we have 2p2. P has 3 degeneracy. This guy does not even have up to half, yet this guy is full, and they are in the same class, 2, 2. They are in energy level 2. So we need to ensure that everybody has at least half. You should be your brother's keeper. So that's what will make this guy say that, okay, half of my magnanimity, let me give you one so that you become at least sufficient enough for all of us to be stable. So this is going to give off one, and the configuration of carbon is going to change to 2s1, 2p3, making it have 4 unpaired electrons. And by doing so, carbon is going to be able to combine with every other element by 4 different bonds. So this is 4 bond pair, and that's what makes carbon tetracovalent. Okay, so it will be able to share these 4 bonds to form a stable compound, either with hydrogen, with nitrogen, with oxygen, and so on and so forth. So one of the first uniqueness of carbon is in tetracovalency, ability to form 4 covalent bonds. All right, I think that is clear. The second thing we must know about carbon is that it has the ability to form multiple bonds with itself. Carbon has the ability to form multiple bonds with itself. That is, it can form single carbon to carbon bond. Okay, it can form double carbon to carbon bond. It can form triple carbon to carbon bond with itself. And not only is it able to form it with itself, and most importantly, they are going to be stable. Okay, think about other things like silicon and the likes of them. They can form double bond, they can as well form other kind of bond, but the stability is what distinguish, is what differentiates stand out. This is as a stable formation, a stable element that can form multiple bonds. So the ability bond is another unique property of carbon. All right. Now, another unique property of carbon that we should study is called catenation. Catenation. Okay. So catenation, what exactly do you mean by catenation? Okay. Catenation is the ability of carbon of an element, essentially. In this context, carbon, ability of carbon to form straight chain, branch chain, or even ring form compounds. Okay. So you think about certain compounds that we come across when we are looking at organic chemistry. Subsequently, you see something like a carbon that is like this, okay, and it's a single straight chain. This is what I mean by a straight chain. And if I want it to be a branch chain, instead of going straight, I can have it branched. Okay, so this is branch chain, and this is going to be stable only because it is carbon. It has the ability to undergo catenation. All right. So the first one, tetracovalency. The second one, formation of multiple bonds. The third one, catenation. All right. So those are the three essential things that are relevant when it comes to looking at the uniqueness of carbon in organic chemistry. There may be other ones, of course, I'm quite aware, but if you read the other ones listed in your textbooks, they have all been summarized into the 3 points that I gave you. So if at all you forget anything, number one, there are certain uniqueness of carbon that makes it applicable to have a particular branch of chemistry dedicated to it alone. The first is it is tetracovalent in nature. The second is that it can form multiple bonds with itself and other elements. And the last one is that it can undergo catenation. All right, now that we know about the uniqueness of carbon, let's move on. Say Tabati Morawa, we should actually look into, okay, learning how to relate with each other. That is, for those that are non-Yoruba speaking, once you know me, the next thing is to be able to study and know my behavior, my character. So that what leads me now to what we are going to study next, characteristics of organic compounds. Characteristics. So what are some features or characteristics that you expect to see in a typical organic compound? Number one, organic compounds are generally non-polar. Organic compounds are what? Generally non-polar. That is, they do not have poles and therefore do not dissolve in water. You know, water is a polar covalent compound. So as such, we expect that according to the rule of solubility, like dissolves like. So soluble will dissolve soluble, insoluble will dissolve insoluble, polar will dissolve polar, non-polar will dissolve non-polar. So because organic compounds are generally non-polar and water is polar, so there will not be readily soluble, if at all there are any soluble in water. All right, that's the first thing we should know about the characteristics or properties of organic compound. Number two, you must know that organic compounds have low melting and boiling points. Organic compounds have low boiling and melting points. You know, it's actually a covalent compound, and we know unlike ionic compounds that have high melting and boiling points, covalent compounds, which in this context of organic compounds, they have low melting and boiling points. All right, we leave that. Number three, of course, organic compounds are volatile. They have high volatility. Now, what exactly do we mean when we say a substance is volatile? Volatility describes the ability of a substance to become a vapor, that is, to escape as a gas. So, organic compounds are generally in nature. All right. So, that's another one. Now, of course, there are other things that you may want to know. For example, organic compounds are flammable and the likes of them. Okay. There are common uses as industrial solvents and so on and so forth. So, but I think the major things that you must first know about organic compounds, of course, they are non-polar, that is, they are not readily soluble in water. Number two is the fact that they have low melting and boiling point, and of course, the fact that they are volatile, they are flammable, and so on and so forth. Now we know about organic chemistry, we know about the uniqueness of carbon, we know about the properties of organic compounds. We move down straight up to look at what are the branches that we have for organic compounds. All right, so I think I will switch my board a bit. I'll switch my board slightly. I need to switch. Sorry. Okay, I need to switch my board slightly. I need to draw a flowchart. All right. So for I want us to always remember this flowchart in our discussion. So we are going to organic compounds. Now, our organic compounds, we have it divided into two broad bases. So we have, well, there are different ways by which you can classify organic compounds, by the way. So I want to go with the pattern of homo atoms and hetero atoms. Okay, heteroatoms. All right, now for your homoatoms, of course, those are the ones that have only similar kind of atoms. That is, they fall under the category of your hydrocarbons. So I kind of see them as hydrocarbons. It's just carbon and only one element, but here more than just carbon and one atom. All right, so under your hydrocarbons now, okay, well, then let me call them hydrocarbon. Okay, you know what? The best option is not to go with homoatomic. It's going to give us issues. So let's go with the other classification. So we go with aliph. No. Okay, acyclic and cyclic. Okay. Now, your acyclic compounds are compounds that do not form cycle. Okay, and those that are cyclic are those that form cycle. All right. I think I'm skipping something before getting here. We should have aliphatic, and then we have aromatic. There are quite a number of classification methods that we can have, but I'm having quite a number of classifications coming to my head right now. So that's why I'm trying to see the best option to go with. Okay, so I actually have another classification here that we may want to work with. We have open chain and closed chain. So, but I'll put them under aliphatic and aromatic. So we have aliphatic. Now, under your aliphatic compounds, you can have it divided into the acyclic and cyclic. Okay. Now, the acyclic is otherwise called open chain. Okay, and the cyclic is otherwise called closed chain. Okay, so now for your aromatic, of course, those are like benzene containing compounds. There can be the pure benzene, and then we can have benzene derivatives like those other ones that have other elements, toluene, phenol, and the likes of them. So now, under your open chain, that is the ones that are not ringed or circular, we want to think about the major hydrocarbons and non-hydrocarbons. So for your hydrocarbons and then non-hydrocarbons. Okay, under hydrocarbons, these are compounds that contain just carbon and hydrogen. That's why we call them hydrocarbons, hydrogen and carbon. So you have the first and most prominent organic compound, the alkanes. Then we have the alkenes. We have the alkynes. Okay, now these are the most prominent acyclic hydrocarbons that you want to think about. Now, other ones that are acyclic, that is, that they are not cyclic, but they are not just hydrocarbons. You have your alkanols. Okay, sorry, you have non-hydrocarbons. Now you want to think about your let me see, alkynes. Apparently, those are the categories we can have. We should not be able to have something here. So under your cyclic now, let's go to your cyclic. We'll have the ones that are closed chain. Of course, in this case, benzene can also be a hydrocarbon, by the way, but I'm not putting it here because it's acyclic. So benzene is also a hydrocarbon, just in case. So here we are going to think about compounds that are cyclic. Of course, your aromatics can also fall here, but just that they are not aliphatic. So you want to also think about your alkanols. Okay. You want to think about your, I'm trying to get something across now. The cycloalkanes, yeah. So you have your cycloalkanes, your cycloalkynes, and every other compound that is basically rings. Okay, now before I skip out, we have non-hydrocarbons. Okay, so they would actually fall in here. You think about alkanols. Okay, alkanols is having ROH. So of course, it's not only carbon and hydrogen, that's oxygen. So it's a non-hydrocarbon and of course aliphatic acyclic. You want to think about your alkanals, your alkanoic acid, your alkanones, your cyanonitrals, and so on and so forth. So we are going to be exploring each of those families or classifications subsequently over time. All right, now that we have a bit of picture of what we expect to see in the classification of organic compounds, I think we should move next down to talk about the terms in organic chemistry. But before we go to that, if you recall questions on what we've said so far, we said organic compounds are organic chemistry came up with vital force theory, and of course, we talked about some of the uniqueness of carbon, and then we moved on to look at some of the properties of carbon that makes it unique. We talked about tetracovalency, we talked about formation of multiple bonds, we talked about catenation. Now, after that, we went on to talk about the properties or characteristics of organic compounds. We started off with low boiling and melting point. We talked about non-polarity. We talked about volatility of organic compounds. We talk about them being flammable like that, and so on and so forth. Now we move down to talk about the classifications, and we've talked about the fact that they can be aliphatic or aromatic. Now, if it is aliphatic, it can be open chain, which is acyclic, or closed chain, which is cyclic. So for your open chain, we want to talk about your hydrocarbons and hydrocarbons. Hydrocarbons, those that contain carbon and hydrogen only. And that's where you have your alkanes and alkynes. And of course, your other end, you have your alkanols and so on. Then you cyclic ones, and then we move down to the aromatic. All right. So the next thing now, we want to look at the terms of fundamental concepts in organic chemistry, the fundamental concepts in organic chemistry. Okay. So for the fundamental concepts now, before I move into the fundamental concepts, it is important to be able to distinguish organic compound as being saturated or unsaturated, as it's also a means of classification. So I'll be starting off with test for unsaturation or test for saturation. So organic compounds may actually be saturated or unsaturated. Now, what do I mean exactly by that? There are certain things that we can use to check if organic compounds are saturated. The first thing and the most popular one is to use your bromine water, use of bromine water. So in order to test for saturation, we use bromine water. Now, what do we expect to see when we use bromine water? If a compound is saturated, decolorized means to remove color. So it means that we are turning whatever stuff to become colorless. So if we say unsaturated compounds will decolorize bromine water, means they will change bromine water from whatever color it is to what? To colorless. They will remove the color of bromine. All right. So if a compound is saturated, it does not decolorize bromine water. Okay, but on the other hand, does it mean it is only unsaturated compounds that will not decolorize bromine water? No. That is why you must note that benzene, although unsaturated, does not decolorize bromine water. Again, benzene, although unsaturated, does not decolorize bromine water. So if you have a question that says a particular substance X does not decolorize bromine water, you may want to consider your saturated compound, which is majorly alkanes. Okay, alkanes are saturated organic compounds and they do not decolorize bromine water. Okay, so however, aside alkanes, your aromatics, benzene also does not decolorize bromine. Unsaturated ones. And what will be the effect on bromine water? The unsaturated compounds, they will definitely decolorize bromine water. You don't talk about your alkenes. Alkenes will decolorize bromine water. You talk about your alkynes, they will decolorize bromine water. Okay? Then your cycloalkenes and cycloalkynes as well, they will also decolorize bromine water. So a particular question comes in the form telling you that an organic compound is unknown. However, in order to identify it, bromine water was passed through the organic compound and it was observed to decolorize bromine water. The organic compound is likely dash. So your answer can either be an alkene or an alkyne, but of course it can never be an alkane, cannot be a cycloalkane, neither can it ever be a benzene. All right, so that's on that for saturation and unsaturation of organic compounds. Okay, so we move on from there. How else can we test for unsaturation? How else can we test for unsaturation? Okay, so we've outlined bromine water. The next thing we want to use acidified KMNO4. Okay, that's your permanganate. So this one we say it's changed from brown to colorless. We are decolorizing. So the same thing with this, it will also decolorize it. It will change it from purple to colorless. Okay, so from purple to colorless, that's for acidified KMNO4. So if an organic compound changes acidified KMNO4 from purple to colorless, it is what? Unsaturated. Also, the next one is using acidified K2Cr2O7, which is your potassium heptaoxo dichromate 6. What will happen? You remember OG, it changes it from orange to green. Okay, so you don't call yourself an OG and you don't know what happens when an unsaturated compound is changing or detected using K2Cr2O7. So if you're an OG, you should know this in organic chemistry. Now, there are three ways to identify unsaturation in organic compound. Number one, using bromine water. Number two, acidified KMNO4. Number three, acidified K2Cr2O7. Also very important, especially to help you identify an aromatic compound. They will burn with a smoky or sooty flame. Smoky or sooty flame. Okay, so if it is unsaturated, it will burn with a smoky, sooty flame. Okay, now what exactly do I mean by smoky? The smoke is going to be dark. Okay, it's going to be sooty. It will have soot and it's going to be dark. So that's what I mean. So it is especially notable for benzene and aromatic compounds. We get okay. So that's what we have in the case of testing for unsaturation. Now you may also want to rank them. You may also want to rank them that is an issue. Okay, you may also want to rank them in terms of how much smoky flame will they give. So alkane will give us the least smoky flame. So it is less than you see in your alkenes, less than you see in your alkynes, and then the one that is greatest will be in your benzene or aromatics. So this is for increasing smoky or sooty flame. Increasing smoky or sooty flame. Okay, now aside this, don't forget that benzene and alkanes do not decolorize bromine water. All right, now that we know that, I think it's safe to move down to the next part of our business because you have to be conscious of time. Homologous series. Homologous series. All right, so for homologous series now, that's an important part of organic chemistry. What exactly is homologous series. So we define homologous series as a family of organic compounds which follows a regular structural pattern in which each successive member differs by CH2. Now I'm going to take it in steps so that we can have a good grasp of that definition. And if maybe you sleep off and someone pours you hot water and you wake up, they ask you what is homologous series, you should be able to, without blinking twice, tell us the definition. So we say homologous series, the first thing is that it is a family. Okay? Family of what? Organic compounds. Family of organic compounds. What happens to them? Family of organic compounds, they follow a regular structural pattern. That is, if you see the father and we see the son, the shape of the nose, that's the structure. It is similar. And then by the time you see the firstborn, you see the secondborn, you see the thirdborn, you see the fourthborn, they have something in common. That is what we mean by following a regular structural pattern. So family of organic compounds, the family of Mr. Ajanle Koko, that follows a regular structure of having big nose, follows a regular structural pattern. There's no spaces. I'll clean this outline. Okay, so in order to make space, I think I have to clean the outline so that we have enough space to write. So yeah, definition of homologous series now. We say homologous series is a family of organic compounds, okay, which follows a regular structural pattern, which follows a regular structural pattern in which each successive member differs, okay, from the next by CH2 group or relative molecular mass of 14. All right. So organic chemistry, homologous series. We say a homologous series is defined as a family of organic compounds which follows a regular structural pattern in which each successive member differs from the next by a CH2 group. So like I said earlier, it's a family and they follow a structure. Everybody has something in common. Now, but each successive member, firstborn, secondborn, thirdborn, for some parents, they give 3 years between their children. So the firstborn and the secondborn, the difference between the firstborn and secondborn is 3 years. The difference between the secondborn and the thirdborn is 3 years. The difference between the thirdborn and the fourthborn is 3 years. The difference between the fourthborn and the fifthborn is 3 years. And children, you get. So each successive member, in this case of organic compound, regardless of the number of children that a family has, each member differs by CH2. So for example, I do not know what the compound is, but the child told me that the first member is CH4. Okay, so this is the firstborn of the family. So the person that will come after this guy must be different by CH2. So I will add CH2 to this guy 3 years before I give birth to this guy. So CH2 plus CH4, CH2. So C will add to this C to become C2. H2 will add to this to become H6. CH4 plus CH2, that gives us C2H6. So this is going to be the second bond. The difference between this first bond and second bond is CH2. So the third bond now in this case will also increase by CH2. So it becomes C3H8. So that is the definition that it is a family. All of them, they are in a family. They follow a regular structure. What regular structure? Each member that is in that family is different from the next by what? CH2. CH2 group. Now, the CH2 group, I now said, or relative molecular mass of 14. Now, the relative molecular mass of 14 that I'm talking about here, how did we get this 14? CH2, carbon is equal to 12, hydrogen is equal to 1, but we have 2 of it, Abi? So, 12 plus 1 times 2, 2, that's what? 14. That's how we say relative molecular mass of 14. So, putting all of that together, If they wake you up tomorrow morning and they say Francisca, and they say Alapi, and they say Giwa, what is homologous series? We say that homologous series is a family of organic compounds which follows a regular structural pattern in which each successive member of that family differs from the next by what? CH2 group. So I'm going to give you a task now, and I expect everybody to be a part of that task. So you are given a particular organic chemistry family. The member of that family, the third member of the family has the formula C3H7. I am not interested in telling you the name of the family now. Okay, so I give you an unknown family of organic compound C3H7. This is the third member of the family. Now tell me what is going to be the formula of the fourth and fifth member of this family. So see what will I have here? Okay, so tell me what will be the fourth member, what will be the fifth member. Kindly use the chat box very quickly, just 1 minute, to tell me your answer. What's going to be the fourth member? What's going to be the fifth member? I'll be checking the chat box and I'm hoping to see your answer. So okay, Fumilayo, C2, H2N plus 2. No, that's not the formula of the fourth member. The inner weapon. I like your weapon. Oh. Okay, if you ask your own is C4H9, that's for the fourth member. What will happen to the fifth member? Adeyeye, C4H9. C4H9 is correct. Success Emmanuel, C3H8 is not correct. We are looking for the fourth member. Adeyoye, Juliana, you are correct. Okay, Tijani, you are correct. James Wisdom, okay, yeah. Adeji, I've seen your answer. That's for the fifth member. Papi J. Okay, yeah, I'm feeling that your name. Enoch Steven, that's the fourth member. What's going to be the fifth member? Ayomide, Omotomiwa, Zainab, Fumilayo. Okay, your answer is correct. All right, let's move on. So, like most of you have rightly gotten it, if you do not get it well, I advise that you pay attention and understand the simple logic. We have not even done any major stuff here. We are only trying to get the concept from the definition of homologous series. So the third member in this family, the family of Mr. Onoguneru, or whatever name you want to call it now. Okay, so the third one in that family is C3H7. Now, the next member should increase by what? CH2. Okay, so when I add C to C3, it becomes what? C4. When H2 to 7, it becomes H9. So the fourth member is C4. So let's go to the fifth member. I'm going to add CH2 to the fourth member since that is the successive. What successive means? The one that follows the next one. They are following each other. After 1, the successive number is 2. After 2, the number is 3. After 3, the number is. So H, the number you add C here becomes C5. When you add H2 here, it becomes H11. All right, that's how to determine the members of your homologous series. So it works for any family of organic compound. I want to believe that it is very clear to you. So I want to give you another example quickly. You drop it in the chat box, and I may not be able to exactly check because of our time, but you can write it somewhere and go back to check. Okay. So a minute, need to set up my lights. All right, we move on from there. We want to talk about the other example I wanted to give you. So we have something like C2H6. This is the second member. This is the second member of a homologous series. So my question to you now is, what do you think is going to be in the next member, the third member? What should be the third member of this family? What should be the third member? Sorry, put it up. Okay, so what should be the third member of this family? What should be the third member of this family? Quickly. All right, C3H8, definitely. So I'm just bringing this up for the sake of those that do not get it. So CH2 is what we are adding. So if you add this, becomes C3, H2 to this becomes H8. So C3H8. Now we are good to go with the concept of homologous series. Each successive member differs by CH2 group. Now, beyond that definition, there are some other things that we should know about the homologous series. Okay, there are some other things that we should know about the homologous series. That talks about some of the characteristics of the homologous series. So the first thing is, of course, in the definition, each or relative molecular mass of 14. That's the first thing that comes to mind. Now, the second thing that comes to your mind now is in terms of the properties. Okay, because they are a family, every member of that family have the same DNA. Abi, they have similar genotype, rather, not DNA. I mean, no two humans have same genetic composition exactly. So, but what I'm trying to bring up here is, people should not disturb me in biology. So, what I'm trying to bring up here is that members in a particular family, they have something in common. You get? So, in this case now, members of the homologous series have similar chemical properties. I've given number one. Number one is that each member differs by CH2 or relative molecular mass of 14. That's the first characteristics of homologous series. Okay, so number one, each member differs by CH2 group. Number two, okay, I'll probably use it. All right, so number two now, we said for the second one, they have similar chemical properties. Okay. That means for their physical properties, you expect something different. But of course, for their chemical properties, it's going to be similar. Okay. Now, those physical properties that are now or that is varying, what are the things that we must know about them? So the first thing is in terms of boiling point. So we must know certain things about the boiling point of homologous series. We must know some things about the boiling point of homologous series. So the first thing is in terms of the number of carbon atoms. Okay, as you go down the group on your homologous series, the number of carbon atoms continue to increase. So because the carbon atom is increasing as you go down, then there will be an effect on the boiling point. So the idea is that when the carbon atom is increasing, the boiling point is also increasing. Okay, so because the boiling point is increasing, you can say it is directly proportional. That makes me want to explain the concept of proportionality. Okay, we can have something as in your variation, we have direct proportion, directly proportional, inversely proportional, partial, and joint variation, as the case may apply. So my concern here is direct and indirect. If something is directly proportional, it means when one increases, the other increases. So if I say A is directly proportional to B, it means when A goes up, B also goes up. However, if I say A is inversely proportional to B, it means when A goes up, B should go down. Okay, so if carbon is increasing, the boiling point increases. You can tell already that that is going to be directly proportional. So increase in number of carbon atom, increase in boiling point. So that is why they are directly proportional. So if I give you a compound, let's say for example, we have a carbon atom, we have 3 carbon atoms, and we have 4 carbon atoms. Which one should have the higher boiling point? Obviously, that's going to be C4H10. Why? Because the more the number of carbon atoms, the more the what? Boiling point. So carbon atom is directly proportional to boiling point. There is no debate around it. Okay, now that's the first thing. The second thing is that, of course, if the carbon atom is increasing, for example, C3H8, now C3H8 and C4H10, if you calculate their relative molecular mass, C3 is carbon is 12, 12 times 3 is 36, 36 plus 8 is 44. That's the relative molecular mass of propane. For this one, C4, that's 48, plus 10, that's 58. You can see that the relative molecular mass is increasing. The more the carbon atom, the more the relative molecular mass. So therefore, we can as well see that the relative molecular mass can also increase. Now, what is the relationship between the relative molecular mass and boiling point? The same thing. So the more the relative molecular mass, the more what? boiling point. They are also directly proportional to one another. Okay. Now, if I give you a compound that has relative molecular mass of 48 and another one that has relative molecular mass of 60, and I say which one will have a higher boiling point, you expect that one that has 60 to have higher boiling point. The more the carbon, the more the boiling point. The more the relative molecular mass, the more the boiling point. Now, the other thing is to look at it in terms of the branching. Okay, earlier we said that one of the uniqueness of carbon is incatenation. Okay, ability to form straight chain, branched, or ringed compound. So if I have a compound like this is my organic compound, and then I now have another compound, the same 4 carbon. Okay, let me make it 5 carbon. I now have another 5 carbon atom, but my 5 carbon atom is now having a CH3 at the top and another CH3 under it. Okay, so this same molecule, let me separate them. So this same at the top, and if you look at it, 5 carbon atom and C5H14. That's what we have here. Here too is C5H14. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. The same 5, 5. But however, the arrangement is different. This is branch, this is straight chain. So if we want to check for the boiling point now, which one should have a higher boiling point? The idea now is that branching is inversely proportional to the boiling point. Meaning, when branching goes up, boiling point goes down. Okay, so boiling point is inversely proportional to branching. So in that case, for this question, if this is A and this is B, which one should have a higher boiling point? Of course, A will have a higher boiling point because B is already branched, the boiling point would have reduced. So the more the branch property of compound, when we were studying the characteristics of organic compound, we said organic compounds are volatile, that is, they have volatility, ability to become gas. Now, branching is directly proportional to volatility. We want to do a bit of mental work now. Branching is proportional to volatility. Listen properly. Branching directly proportional to volatility. Now, what exactly does this mean? It means when we increase the branching, it becomes more volatile. When we increase more volatility. Abi? So in that case, if branching is now inverse to boiling point, what do we expect that will happen between volatility and boiling point? What I'm trying to bring up here is that branching and volatility, they go in the same way. They are friends. However, the branching itself is an enemy of boiling point. Branching and volatility, friends. Branching and boiling point, enemies. So we usually say that the friend of my friend is my friend, and the enemy of my friend is also my enemy. So by virtue of that, if branching is inverse to boiling point, but it is a friend of volatility, that means volatility will also be inversely proportional to boiling point. Okay, so more volatility, less boiling point. Do you get it now? So that's the case, but please note that branching is directly proportional to volatility. So the more the branching, the more the volatility. Now you must also note that the more the volatility of a fuel, the better fuel it is. If a fuel is more volatile, it makes it a better fuel, although volatility should not be too much so that we don't end up with a knocked engine. Okay, to be volatile. Okay, these are the 4 variations that I think are important for us here in the physical properties in a homologous series. Don't forget, the first point is that they have varying relative molecular mass of 14 or differ by CH2. The second is that they have similar chemical properties. Now, the different physical properties. Out of that physical property, we've picked one now, boiling point. How exactly does boiling point change on the homologous series? The boiling point is proportional directly to carbon atom and relative molecular mass, but is inverse to branching and volatility. All right, I think that's a bit clear. We shouldn't spend all of the time there. Another property that we would want to look at is the trend of the state of matter. So we know, or even if you don't know before, we are learning that now. On any family of organic compound, carbon 1 to carbon 4 are usually gases. Carbon 1 to carbon 4 of any homologous series. So you have our and it's carbon 2, C2, H whatever is going to be a gas. If I have carbon, it's going to be a gas. carbon 4 liquids. Okay, and then anything greater than 18 is going to be solids. Okay, so this is a trend for the state of matter of organic compound. Carbon 1 to 4 gases, 5 to 18 liquids, greater than 18 solid. So if I give you an organic compound C3H6, what is the likely state of matter you expect it to be gas? I said there's an unknown organic compound X that decolorizes bromine water and gives us a smoky or sooty flame, and it happens to have the formula C3H6. What is the likely state of matter? Because it's carbon 3, what do you expect? It will have to be gas. However, I said that an unknown organic compound X does not decolorize bromine water, KMnO4 or K2Cr27, and then it also does not burn with smoky or sooty flame. Now, on checking out the particular organic compound, the formula was found to be C18H30, okay, let's say C20H42, okay, C20H42. This is an alkane, okay, but that's not even your business. Although I've mentioned that it does not decolorize bromine water and all that. So what do you expect to be the state of matter? It's going to be a solid, right? C20H42. I don't know whatever is wrong with YouTube that is making it small, but you guys have to bear with me on that, because I mean, these are the biggest form of my handwriting that you can come across. Okay, so C20H42 solid. Now that we know about this, of course, for our homologous series. YouTube has started with their blurring of our net board, and I exactly don't know what is the cause, but hopefully you guys just need listen to my audio, and we work with that. All right, so we've talked about the state of matter. Now there's also something that we should know about: solubility. Yeah, we must know about the solubility, the trend of homologous series. So for solubility, the solubility is decreasing when we increase the carbon atom. That is, the heavier a molecule is, the less its solubility. Think about it as, not to actually shame anybody, but think about it as a fat and let's not call them thin now. Let's call them moderately sized. So for example, now look at my perfect, body size. Okay. Now, if I jump into water now and size jumps into the water, who do you think will dissolve? Okay, of course, you know that it's easier for me to wade through the water compared to somebody of this size. So it tells you that because they are broken atom, they are going to be insoluble in water. The water self does not like them inside it because they are too big. They're just going to be disturbing the water. However, for people like I have normal little statured body, you observe that it's easy for us to not disturb the water. The water is attracted to us. So what I'm trying to bring up there is that the more the carbon atom, or the more the relative molecular mass, okay, the more the carbon atom or relative molecular mass, it is inverse to the solubility. That means solubility does not carbon atom or relative molecular mass. Do you get? Okay, so that is for solubility. So the more the carbon atom, the lesser the solubility. The more the relative molecular mass, the lesser the solubility. So if I give you these two compounds now, I give you propane, and then I give you propane is carbon 3, pentane is carbon 5. Which one should be more soluble? Obviously, your answer should be what? Propane, carbon 3, because the more the carbon atom, the lesser the solubility. All right. Now, ultimately, there's now one bad guy called the hydrogen bond that you must have known about. Hydrogen bond does not want to know whatever is wrong with you. What it only wants to hear is that in terms of solubility, when there's hydrogen bond, it's going to be soluble. In terms of boiling point, when there's hydrogen bond, it's going to have high boiling point. Do you get? So hydrogen bond confers both solubility and high boiling point on organic compound. And the most popular question I come across there is, in case of alkanols, they said that the general solubility of alkanol is due to dash. Your answer is what? Hydrogen bond. Normally, alkanol is an organic compound, and organic compounds are non-polar. They should not be soluble. But because of hydrogen bond in alkanols, they are going to be what? They are going to be soluble. So the solubility, general solubility of alkanol is what? Hydrogen bond. Also, the high boiling point that you come across is also due to their high boiling point. Now, I think we are going to go. The last characteristics of homologous series that we should know is that all of them have similar general methods of preparation. They have similar general method of preparation. That is, all alkanes, if you want to prepare them, they follow the same pattern. All alkanes same pattern. They have similar general preparation. That is for your homologous series. All that being clear, a quick recap: a family of organic compound which follows a regular structural pattern where each successive member differs by CH2 or relative molecular mass of 14, and we've learned about some of the properties of the homologous series. Now, the next thing that we have on the list is where we're going to have a little bit of work, which is the functional groups. I'll try as much as possible to move very fast because the time is not on our side. Okay, functional groups now. I want to talk about functional. I'm very sure this is not the first time you'll be hearing the word functional groups. Okay. Functional group, they will decide the function of the family. Okay, and the function of the family is measured by the chemical property. So the first thing that comes to your mind as a function of the family is the chemical property. So if we are in a group that does the same function, that means we have similar chemical properties. So you can infer that functional groups determine chemical properties. Functional group determines chemical properties. Okay, functional groups determine chemical properties. So it tells you that if homologous series have similar chemical properties, that means each homologous series have the same functional group. For example, alkanes, all of them have single bond. Single bond is their functional group. That's why they will have similar chemical properties. Alkanes, they have double bond. Double bond is their functional group. That's why they have similar chemical properties. So homologous series have the same functional group, and that's why they have similar chemical properties. So functional groups determine chemical properties. But what exactly is this functional group? By definition, functional group can be a bond. Like I said, for alkanes, the single bond is the functional group. Functional group can be a bond. It can be an atom. For example, where you have ROR. The functional group here is the O. You get, this is an atom of an element. It can even be a group of atoms of elements. For example, ROH. OH is a group. It's not one element. It's two elements now. So it can be a bond, it can be an atom, or even a group of atoms. You get, it can be a bond, an atom, or a group of atoms. That does what? That determines the chemical properties of homologous series of organic compounds or family of organic compound. Okay, so that's what a functional group is: a bond, an atom or group of atoms that determine the chemical properties of homologous series. Now we're going to learn quickly some of the common functional groups that we have. But before I go to that, if functional groups determine chemical properties, what will determine physical properties? If you know it, drop it in the chat box. I'm going to get back to that. So, but we know functional groups determine chemical properties. So the first functional group that I want to talk about is the alkyl. Okay, the alkyl. Although we should be okay. Let's start with the first guy being alkane, because every other functional group that we have comes from these particular guys. Okay, let's try and make something bigger. So we have alkanes. All right. All right, so for alkanes now, their own functional group is the single bond, C to C single bond. That is their own functional group. Okay, so, and that now brings me back to quickly explain to you. Anytime you want to draw an organic compound, because many of you have a problem with drawing organic compounds, the principle is that each carbon must have 4 bonds. Okay, so if I want to draw this carbon now, this compound, I already have a bond here. So this carbon, 1, 2, 3, 4. For it to be single bond all through. If I wanted it to be double bond, if a double bond here, this is 1, 2 already. So 3, 4. I cannot put something down here because that will make it 5. We say carbon is tetravalent. So if you already had 1 bond here, becoming pentavalent. So in the case of alkanes now, single bond, this is 1, for this same carbon 2, 3, 4. Okay, so now this compound is correct and complete. What will be the formula? How many carbon? 2 carbon. C2. How many hydrogen? 1, 2, 3, 4, 5, 6. C2H6. Okay, that's your alkane functional group now. Single bond. So the name of the homologous series is alkane. The functional group is what? Single bond. Homologous series is what? Alkane. Is the alkane family, but the functional group is what? Single bond. Okay. Now, it's also important to know the first member. The first member of your alkane is CH4, which is called methane. Some people don't have methane. That is why it's important to know the first member. So the first member here is methane, CH. So one for alkane. The second one now is alkenes. Alkenes. Okay, so for your alkenes, you still see to C, but this time around it's a double bond. So what do you expect now? This is C double bond. You have 2 already out of the 4. So I can put the third one here and the fourth one here. It does not have to be like that. I can decide that I want to put it here. I can decide that I want to have it like anyhow you want to draw it. It must just not be more than 4. So I'll come here to, I'll do the same thing. If I've seen a student drawn their own like this, they put this one down, they put this one up. I don't know what style you are trying to prove. If it's chemistry or art, but that's not my business. As long as you are obeying the tetracovalency, finance to training GSS2 to machine organic chemistry. All right. So the functional group in this case is the double bond, C to C double bond. All right. So we'll move down quickly to the next one, which is your of course alkenes. Now that reminds me, your alkenes, the first member can never be methane. Because how does carbon want to form double with itself? It's not possible. You know, in the case of alkane, carbon will form with hydrogen, but it cannot form double bond with hydrogen. So it means that there must be another carbon for it to form that double bond with. So that is why the first member of alkene is carbon 2. Okay, the first member in alkene is carbon 2, and that is 18. And that makes it important for me to list how to remember the names by their numbers. So if it is 1 carbon, we call that met. So I'll be using alkane as a reference, methane. Okay, if it is 2 carbon, we call that eth. So for alkane, ethane. If it is 3 carbon, we call it prop. So I'll call this propane. If it is 4, I'll call it but. So this is butane. If it is 5, I'll call it pent. So this is pentane. If it is 6, we call it hex. So this is hexane. If it is 7, we call it hept, which is heptane. If it is 8, we call it oct. So this is octane. If it is 9, we call it non. So this is nonene. And if it is 10, we call it dec, which is decane. Let me just add this one as a bonus for ecosane. All right. That's what we're homologous series. Okay. So methane. So if I'm having 2 carbon atom now for alkene, I expect that it will be what? 18. 18. Okay. 18. Not methane. You get now. So we're having 18. Okay. So that's for the second homologous series. The third one, we want to think about alkynes. So for your alkynes, they have C to C triple bond. So if there is 3 already out of 4, that means you add 1 here, anywhere you want to put it, but just 1. Okay, so the functional group is a triple bond, single, double, triple. Now the fourth one, quickly, we have the alkyl. Alkyl. Now your alkyls are known to be formed by the removal of 1 single hydrogen, but it's still single bond. That now reminds me that we need to know about the general formula. Okay, for your alkenes, there's a formula that you can use. You say that CnH2n plus 2. I think Fumilayo was trying to say that in the chat box earlier when I was talking about homologous series. Okay, so CnH2n plus 2 for alkenes. For alkenes, it is just CnH2n. CnH2n. For alkynes, it is CnH2n minus 2. Now for your alkyl, it is CnH2n plus 1. Okay, so you want to think about alkyl. Most times you'll be working with alkyls as attachments. So I say, give me an alkyl. You want to think about the first member. So you tell me methyl. Methyl now, if I want to get methyl, now N is 1. So I will say C1 H2 times 1 plus 1. So that's C1, Abi. 2 times 1 is 2, 2 plus 1 is 3. So the formula for methyl is CH3. If I want to get for ethyl, that's C2 H2 times 2, 2 times 2, 4, 4 plus 1, 5. So I'm going to have C2H5, and so on and so forth. And that's how we have their formulas. Now, moving on to the other major important parts of functional groups, I want to talk about your alkanols. Okay, so for your alkanols, we have their formulas ROH. Now I'll be using R to represent alkyl groups. I'll use R to represent my alkyl groups. Okay, so if I think of you giving me an alkyl now, you can tell me methyl. Okay, so if you give me methyl, I'll put CH3OH as an example of an alkanol. So because CH3 is the first carbon, and that's what met, so I'll call this methyl. Methyl with OH becomes, instead of calling it alkanol, I don't call it methanol. Okay, just like alkyl is called methyl. So met, then instead of il, it becomes anol. So this becomes methanol. So if you give me ethyl as my alkyl group now, ethyl is second, C2H5. So C2H5OH, because it's et, I'll call it ethanol. Okay, ethanol, apparently. So ethanol, we have that here. So that's the case for your alkanols. And of course, you should be able to draw the structure properly. So the functional group in alkanol is your OH. So any compound that has OH and single bond is an alkanol. So yeah, I give you this compound now, and I say, what is the name of this compound? So I put OH here. Now I said, what is the name of the compound? I open the name of the compound shown below. This is Abi, what do you expect it to be? You expect it to be prop. Okay, let me clean the upper part so that we have enough space to work. So I'm going to draw that structure again. So this is CCC. Okay, and then I have this, and I put my OH here. So this is 3 carbon. You expect that to be prop, but this is having OH, so it's an anol. Okay, so prop anol. That's the name of this particular compound. 3 carbon with OH. So any compound single bond having OH propanol. If you open it's an alkene, so we say prop enol. But in this case, we don't have any business with that yet. So propanol for your alkanols, the functional group is OH. All right. Now we know about alkanols. We move on to the next one. Talk about your alkanals. Alkanals. Okay. Alkanals are otherwise called aldehydes. Alkanals are also called aldehydes. Okay. So aldehydes is another word for alkanals. Now, what's the functional group? It's usually given as RCHO. Okay, I call it the CHO functional group, the CHO homologous series. So R-CHO. Now, how do we draw it out? Let's say you want to give me an R now. Let's say my R here is an ethyl. So that's 2 carbon now, C2H5. If I expand it, I'm going to have 2 carbon. Don't forget, each carbon must carry 4 bonds. So 2 carbon. The first bond is connecting them. That's 1, 2, 3, 4. This one is complete. 1, 2, 3, 4. Then I have CH, then O. Now, whenever O is at the end or terminal point of any organic compound, it always carry double bond. Simply because oxygen has 2 lone pairs. So it's all, and 2 lone pair and 2 bond pair. So the 2 bond pair is why you must form double bond. Except there's something at the front. In that case, it's not good. But as long as O is standing alone, it must form double bond. And this C to O double bond is called carbonyl bond. Carbonyl. All right. So that's just by the way. So this is our alkanal or aldehyde now. We've drawn, of course, every place I don't put stuff here is representing H. So this is my aldehyde now. Now, in order to name aldehyde, you think about how many carbon atoms that you have there. So how many carbon atoms we have? 3 carbon atoms. And of course, so we expect this to be what? Propanal. Propanal. Okay? It's an alkanal, 3 carbon, so propanal. Anytime you are seeing CHO, it's an alkanal or aldehyde. All right? So the functional group is CHO. R is just an attachment. All right? I'm moving on to the next functional group. I'll talk about my alkanones. 7, if I'm not making a mistake already. So alkanones. Your alkanones are otherwise called ketones. Alkanones are otherwise called ketones. And for your ketones, they are represented by RCOR. Okay, RCOR. RCOR. Now for RCOR, let's say you give me your first R as methyl, C, and then you give me, okay, this let's say my first R that you give me now is CH3, and we have CO. Now let's say the second R that you give me now is C3H7. Okay, you've given me two different R's now. Now, if I'm going to use them, I would expand my structure. The rule is that each carbon must not take more than 4 bonds. So I'll pick the first carbon, 1, 2, 3, 4. The next thing is a C. The next thing is O. Now, do I want to put O here? Of course, you may want to put your O here, but don't forget that if you put your O here, it's going to form another functional group. So it's better to put your O at the top or below. So I want to use below for my O now, and then I continue. The next thing is C, 3C, Abi, 2, 3. So each one has 4. 1, 2, 3, 4. Now I'm wondering, why am I not putting anything at the top here? This is 1, 2, 3, 4. If I put something here, it becomes 5. So I don't want to put anything here in order not to disobey tetracovalency. So 1, 2, 3, 1, 2, 3, 4, 1, 2, 3, 4. Now we've drawn our structure properly. So after drawing our structure now, we want to name this compound. There is no stress. The first thing is that your alkanones can never be terminal. That is, this double bond O is also a carbonyl bond. It cannot be terminal. Terminal in the sense that it will always be between, because it's RCOR. Now, the idea is that we should count the number of carbon atoms. So how many carbon do we have here? 1, 2, 3, 4, 5. So what do you expect for 5? Pent, Abi. So you should call this pentanone. But the idea is now that the functional group is on carbon 2. So some authors will call it 2-pentanone, some will call it pentan-2-one, and of course, some will just call it pentanone. So it depends on the author. But I believe this should be 2-pentanone. Okay? From your word alkanone. So anytime you are saying RCOR, it's an alkanone also called ketone. Now you must take note in your book that the first member of the ketones group is propanone. The first member of the ketone is propanone, otherwise called acetone. The first member is propanone, otherwise called acetone. The first okay, the first member of alkanal, your question. Now let's try to see. For alkanal, we can actually have HCHO. So that's, what do you think we are going to call this? We call it methanol. Okay, so methanol or methanol rather. And methanol is also otherwise called formaldehyde. Formaldehyde. Okay. So the first member of alkanal, thank you for asking, is methanol, otherwise called formaldehyde. And for your alkanone, the first member is propanone, otherwise called acetone. Okay? I hope I've answered your question. Ozicho baby. Which part of it are you trying to ask? I do not get that. Please use the chat box to clarify. Okay, but for your alkanones, the methanol, met is 1 carbon, Abi, just like we have methane. Methane is like this, 1 carbon now. So 1 carbon atom. So if you want to get methanol, it's also going to be 1 carbon. Now, but just that nothing must happen to the functional group, and the functional group is CHO. Nothing must happen to it. Do you get? So in order to remain 1 carbon, if I should add CH3, it's no longer 1 carbon, it's now 2 carbon. So that in your aldehyde, your R can actually be H, and it can also be any alkyl group, only in this case. But when you come to your propanone, this one can never be H. Do you get? This can never be H. So that's why the first member is what? Propanone. It must have at least 3 carbon atoms. 1, 2, and then maybe a minimum of, the smallest alkyl group is CH3. So that's why the first member in your alkanone is propanone or acetone, but in your alkanal, it can be methanol. I hope that is already clear. All right. So the 2-pentanone. Okay. So let's come back to it. I said it should give me an alkyl group. The functional group alkanone is RCOR. So let's say the first R that you give me now, I don't want to waste time. That's I would have asked you to be giving me R's. So now let's say that you guys give me methyl CH3. Then the second one, you guys give me propyl C3H7. That's what we wrote here. Abi RCOR. Now I'm going to expand my structure, and I have CH3 C H, 3H, but carbon is tetracovalent. So the fourth bond is here. Then CO. I would want my O to be below or above, so that it's going to be a carbonyl bond. Then I continue 1, 2, 3, 4. Then this again, C3H7, 1, 2, 3. Then each one carries the 4 bond. That's the correct structure. Now to name your alkanon, just count how many carbon atoms. This is 5 carbon atoms. 1, 2, 3, 4, 5. Abi? Now, so that's 5. We expect it to be pent. Now, but we need to indicate the position of this double bond. And anytime you want to count or name a compound, you count such that the functional group has the lowest numbering. We've not done nomenclature yet, but this is of it already. So in this case, if you want to count, if you count like this will be 1, 2, 3, 4. So you want to call it 4 pentanone or pentan 4-one. But if you count like this is 1, 2, 3, 4, 5. So it means it is on carbon 2. So you want to call it 2 pentanone. So between 4 and 2, which one is better? You go for 2, the lowest number. Do you get? So the lowest number is why this is 2 pentanone. I hope that clarifies your confusion. All right. So Adereti, I've noted your comment. I'll see if that's a possibility. But maybe we may have another session like this, depending on my schedule and, of course, your response to my task. Because, of course, at the end of this class, I have a task for you. So if you do my task, we may be having another session some day, tomorrow or thereabout. All right, let's go on with our functional groups. We've taken alkanones. The next thing I want us to take alkoxy-alkanes. Alkoxy-alkanes. Okay. Now we have alkoxy-alkanes. Okay, so we have alkoxy-alkanes. Alkoxy-alkanes. All right. So for alkoxy-alkanes, they are otherwise called ethers. Alkoxy-alkanes are otherwise called ethers. Okay. Yes, of course. It can also be called pentan 2-one. I think I mentioned that you can call it 2-pentanone or pentan 2-one. So you are correct. Just like you can say propan 2-ol or 2-propanol. All right. So for alkoxy-alkane, theirs are written as ROR. So if you give me an R, let's say my first R is CH3, then O, then another CH3. So I would want to expand this as CH3, O, CH3. Now, if you look at it, there's no double bond because the O is not standing alone. It is binding to another stuff. So this is not a carbonyl bond. So they say which of the following does not have a carbonyl bond? Alkanol does not. Alkanone has, but these alkoxy-alkanes do not have carbonyl bond. That's another question, by the way. So now, how do we name your ethers or alkoxy-alkane? So the alkoxy is usually for the smaller attachment, while your alkanes on this side. Okay, so your alkoxy, the reflection of that. Okay, so your alkoxy is the smaller one, your alkane is the bigger one. So let's use this side of the board because of the reflection of that light. So I'll bring this structure back here. CH3, OCH3. So CH3, OCH3. So like I said, alkoxy-alkane. The alkoxy is the smaller attachment, the alkane is the bigger attachment. But in this case, we have equal. This is methyl, 1 carbon. This is methyl, 1 carbon. So you can decide to choose anyone as your alkoxy. So in this case, the name of this compound will be methoxymethane. This is my methoxy. This is my methane. Do you get? So that's for your alkoxy-alkane or ether. So if I don't want to call it, this is the IUPAC name. But there's an old conventional way of naming ethers too. So this is methyl, 2-methyl. 2 means di as a prefix. So I can say this is dimethyl ether. If it's not methyl, let's say this one is methyl and ethyl now. Let's assume that I change this thing to become CH3 OC2H5. CH3OC2H5. So when I expand it, I will have CH3OC2H5. So don't forget, the smaller attachment is alkoxy, the bigger one is alkane. So between CH3 and C2H5, which one is smaller? CH3. So this will be my alkoxy. What's the CH3? Met. So this will be methoxy. Now the second one is the bigger one, C2H5, C2, eth. So this is going to be ethane. So this is methoxyethane. Methoxyethane. Now this is the IUPAC system. However, if I want to use the conventional system, I'll say this is methyl ethyl. I have methyl and ethyl, but of course you must go with alphabetical order. So I cannot have M before E. Methyl and ethyl. E comes before M. So this will be ethyl methyl ether. But this is not the IUPAC name, in case you come across it. So that's why it's better to know the IUPAC. The smaller one is your alkoxy, the bigger one is your alkane. So, ladies and gentlemen, what I want to give you now is, if I should swap this thing, what will be the compound? Drop yours in the chat box. So I swap it, it becomes C2H5OCH3. What will be the name of the compound? I'll see your answers and I will move on from there very quickly. Just one or two answers and we are good to go. C2H5OCH3, what should be the name of this alkoxy alkane? Quickly. I just need two answers and I'll move on from here. Sharp. There is no time for us to waste. Yeah. What's the name of this compound? See, when I swapped it, I have C2H5OCH3. So what will be the name of the compound? Okay, ethoxymethane. Okay, ó tún gbé mi débẹ̀, ethoxymethane. Okay, Enoch, I've said your answer. Other answers, I just need one more answer and then I'll move on. C2H5OCH3. What's going to be your answer? Okay, ethoxymethane. Olúṣọlá Adépọ̀jù, ó tún gbé mi débẹ̀. No wahala. Now, no, I do not agree with ethoxymethane. Okay, Funmi Adebayo, methoxyethane. Okay, Tijani, it is still methoxyethane. All right, of course, now the idea is that you should not look at whatever the structure is. The idea is the smaller one is always your alkoxy, regardless of where it is, and the bigger one is your alkane. So for the fact that this one, C2H5 was here and is now here, you should not change it. The smaller one is still methyl. So this is methoxy. The bigger one is ethane. So methoxyethane. When I come here, the bigger one is still ethyl, the smaller one is still methyl. So this is still methoxyethane. So the principle is clear. The smaller one is your alkoxy, the bigger one is your alkane. I hope you've seen the correction to that. And another name for alkoxy alkane is ethers. All right, we've taken alkanols, alkoxy alkanes, alkanals, alkanones. I'll move down to the next one now, which is your alkanoic acids. Alkanoic acids. All right. So for your alkanoic acid now, alkanoic acid. Okay, for alkanoic acid we use RCOOH. Okay, 10 COOH. Okay, alkanoic acid RCOOH. So I'm going to draw the structure out. RCOOH. So this is the structure. There's a carbonyl at the top, and then there's an OH. You get, so it's a combination of carbonyl and hydroxyl. All right, that's for your RCOOH. Okay, so once it's 11 o'clock, it's 11 o'clock. I should make my announcement, and then I'll see if I want to continue or otherwise. All right, so RCOOH, we call that alkanoic acid. Now let's quickly take this example before I make my announcement. So for R now, in this case, what will be my R? What R should I use? Can somebody give me an R? Anybody quickly? Somebody any R use? Bromine or letter R. What R should I use? What alkyl should I use? What alkyl should I use? Quickly. Okay. Enoch said we should use C3H5. That's the first one that came in. So I'll use C3H5, then COOH. Okay. So when I expand this, I'm going to have C3, then COOH. So what do you think is going to be the way to name them? In order to name these ones, just count the number of carbon atoms. So how many carbon atoms we have in total? 4. So and 4 is what? But. So this is going to be butanoic acid. This is the easiest that you are going to come across apparently. So although everything is easy, but it's just about context. So this is butanoic acid. So quickly, for you rightly know that the marathon revision class is ongoing, and of course, the Operation Storm UTME, we've started day 1, day 2, day 3, and day 4 was held, of course, on Thursday, if I'm not making a mistake. So between Monday and Thursday, we've covered 4 days, and each day features 4 subjects. Okay, so I don't know, you may have come across the flyer on your groups or whatever platform by which you got our link, or maybe you actually got it from YouTube. So this is a flyer for the Operation Storm UTME program, where we feature the top scorers, and we are running the 15 days marathon session to cover the whole syllabus. The major reason why we do the program yearly since 2022 is to help you cover the whole syllabus, especially for those that have joined or that started preparing for tutorial very late. So that's the essence of the program. And of course, after making calculations at the end of the program, you would attend 60 classes. And going by the bill for the online session, the class is 7,000 naira. And if you join physically, that's 12,000 naira. So if you calculate apparently for the online guys, you are paying 117 per class, and it's a 2-hour class. For example, in chemistry, on day 1, we will cover matter, properties, phases, and all of that. Go to isotopy, go to separation techniques, rather, all the separation techniques. In day 2, you look at atomic structure, all the quantum numbers and the likes of them. So yeah, and you're paying 117 naira per class. At the end of the day, you are making a total payment of 7,000 naira for the lecture. I actually think that is not too much to pay for knowledge. Now, I've come across many students saying that they don't have the money. So I don't have the money, I don't have the money. And of course, I usually tell students one thing. If you say you cannot look for 7,000 naira to attend a class, to write your JAM class, next year, registration for JAM will still be there. If you fail to learn what you should learn now, and you have a reason to write JAM next year, that 7,000 naira that you don't have today to register for class, you will look for it and you'll be able to pay it to register for next year UTM, which I don't think is ideal. So it's better to do the needful once and for all. Simple. So while you are putting in all of your effort, you need structured teaching in order to help you ace the UTM. So understandable also that it is not the end of the month, and most people are salary earners as well as parents. I mean, this is the Tinubu regime and people are struggling a bit. So we've also come up with strategic payment methods that can help you not miss any part of the class. Just that many of you don't read message on the group, and that is why you missed classes. So I've sent a message across to the group on previous days that you can actually join the classes without making your payment now, provided you have it in mind. Not that you come and I wonder when somebody tells me that I want to join the class, but I don't have money. I mean, what exactly do you mean? You don't have money. So how about the people that have paid? So I'm not telling you to come and join the class if you don't have money. I'm only calling you to come and join the class if you don't have money now, but you intend to pay at most by the end of the month. So, and we can allow you to pay a sum of 5,000 naira now, or you pay 7,000 naira for the class, and by the end of the teaching period, when it's going to be having tests, we are going to have over 2,000 questions for test, and out of which you would most likely come across a couple of them in your exam. So the test part is 3,000 naira, the teaching part is 7,000 naira. It is advisable to attend both of them, by the way. But to start with, you can register for the class and move on from there. So just after the session, feel free to send me a message via WhatsApp or through our official number. So maybe to make it easier, I will put my number here so you can easily send me a message. Just send the word OSU to me, okay, or to the official number. So just send the word OSU registration and it will be duly sorted. Again, it's not a free class. So don't tell me that, Uncle, Dr. J, I want to join, I don't have money. No, there's no free stuff anywhere in the world. So if you see something that is free, you should run away from it. because something is fishy. So yeah, but affordability, and of course, I've seen a 4 days class going for 15,000 in this same online space, but I'm giving you as much as 23 days of activity for lesser price. All right. So, and I advise that you don't miss up. You don't miss so much classes. Classes continue tomorrow. Send a message to that your auntie, that your uncle, that you want to write jam, and you need to register for class. So let's come back to our class while we round up functional groups. So alkanoic acid. So tell me in the chat box, what is the name of this alkanoic acid? So I'll be using one that Steven or something. The second person gave us the alkyl. So he said C2H5, so COOH. So if I C2H5COOH. So what will be the name, the alpha name of this compound? Quickly drop that in the chat box. C2H5COOH. What is your answer? Yeah, and for those of you that are already in the class, so let me drop more fire so that those that are not there, we should not use the fire to burn them, by the way, but they should, of course, join the class. Okay. Oh, you're asking of Banax. If you want to meet Banax, join the class. You see Banax in physics in the OSU class. Banax is not available free class. Banax wants to be paid, so pay money to be a part of Banax classes. So yeah, what's the name of this compound? Propanoic acid. I can see that from Enoch Steven. Of course, absolutely correct. What we just need to do here is count the number of carbon atoms, and that's 3 carbon prop because it's an alkanoic acid. So that's propanoic acid. Okay, that's for alkanoic acid. Quickly, we are almost at the end of functional groups, so we're going to peg it for tonight. So for the next one, I want to move down to alkyl alkanoate. Alkyl alkanoate. Alkyl alkanoate. All right. So for alkyl alkanoate, they are written as RCOOR. RCOOR, and we expand that to be RCOOR. RCOOR. Alkyl alkanoate. They are otherwise called the name of your girlfriend, Esther. Okay, so that's your girlfriend. The only difference is that we removed H from her name, and that's what we call your alkyl alkanoate, esters. All right. So for esters, how exactly do we name them? Well, esters are formed by a kind of reaction called esterification reaction. Esters are formed by esterification reaction. Now, what's esterification reaction? Esterification reaction is the reaction of an alkanol with an alkanoic acid in the presence of concentrated H2SO4. A question comes out asking you what is the work of this. So it is acting as a catalyst and as a dehydrating agent. So the question says, what's the function of concentrated H2SO4 in esterification reaction? It is both as a catalyst and as a dehydrating agent. So now, when this comes together, it gives us alkyl alkanoate. Well, it is similar to what do we call it now? It is similar to neutralization reaction because it's like reaction of acid with base. You know, alkanol is amphoteric. Alkanol is amphoteric. So if you have acid with base to give us a salt, we think about it as a neutralization reaction. We have acid reacting with a base to give us salt and water. So of course, this is also going to give us salt and water. So, but the difference now is that neutralization reaction is irreversible, but esterification reaction is reversible. Okay. Neutralization reaction does not use a catalyst, but esterification reaction uses a catalyst. So that's like a differentiation of esterification reaction and neutralization. Number one, esterification is reversible, neutralization is irreversible. Number two, esterification uses catalyst, neutralization does not use catalyst. Now, let's look at the big picture. So let's say an alkanol, let's say I'm using C2H5OH. So C2H5OH, and alkanoic acid, let's say I'm using C3H7COOH. So what happened is that we remove the OH here in your alkanol, remove the H in your alkanoic acid. So we remove the two of them. OH and H will give us the water. So that's how we get H2O. So what are we going to have left? We are going to have here C3H7 COO. Then what we have left here, C2H5. You get? So that's how to get the structure of alkyl alkanoate. So you remove H and then you put the remaining part of your OH here and add it to the front. That's how we get your alkyl alkanoate. This reaction here is called esterification reaction. So that exactly decides how we name this compound. Do you get? That is what decides how we name the compound. When you want to name, if this one is your front, so you start naming from the front to what? To the back. From the front to the back. You start naming like this. So this first part that you added, the alkanol part is what will form your alkyl. The alkanol part forms your what? Alkyl. The alkanoic acid forms your alkanoate. So now, look at this compound. C2H5OH, that's earth. That's my ethanol. C3H7COH, that's 4 carbon, butanoic acid. So if I use it to form an ester, I will start with my alkyl, which is an alkanol. That's what it. So I'll call it ethyl. Then this is how many carbon? 4 carbon. I'll call it butanoate. Okay? Look at the idea again. Your alkanol is your alkyl. Your alkanoic acid is your alkanoate. Okay, so the alkanol here is ethanol, so it is ethyl, it's one at the front. Then your alkanoic acid is butanoic acid, so this is butanoate, the one at the back. So whenever you want to name your alkyl alkanoate, the one at the front is your alkyl, the one at the back is your alkanoate. So quickly, what will be the name of the alkyl alkanoate formed when I have CH3, COO, C2H5? Okay, I'm going to solve that because of time. So the one at the front is C2H5. So this is ethyl. Then how many carbon atoms we have here? 2 carbon. So this is going to be ethanoate. So if we put that together, we call this ethyl ethanoate. That is the name of this compound. Ethyl. Your own question, your business is, if I swap this, I pick this one, bring it to the back, it becomes C2H5, COO, and then I pick CH3 to the front. What will be the name of this compound? Quickly use the chat box and tell me your answer. I think we are about the end of it already. We have 2 more functional groups, which we not even have to name, and that's everything functional group that we need to know. So what's the name of this compound quickly? Ethyl ethanoate. Enoch does not understand. Okay, ethyl ethanoate, that's from Jenny Marcel. Okay. Okay, that's for the previous one. Okay, Jenny says it is methyl propanoate. Okay, that seems correct, by the way. The name of the ester, or go and look for an ester. So when you give birth to an ester, about the B ester, you'll be able to understand it properly. But don't worry, I will find you an ester. My sister's name is Esther. So if you can pay the bride price, I will let her marry you. Methyl propanoate as Abibulai. Medera, you don't understand too. All of you that don't understand, 300 tubers of yam. Come and marry my sister that is Esther, so that you can understand how to name Esters. All right, so I'm going to draw it out as usual. But even before drawing, this is the one at the front. What do you call this one? Methyl. This is the one at the back. How many carbon is it? 3. That is what? Propyl. Let me just call it propyl. Now I said the one at the front is your alkanol, and it is one that will form your alkyl. The name of ester is alkyl alkanoate. So the one at the front is your alkyl, the one at the back is your alkanoate. So if the one at the front is methyl and the one at the back is prop, so what do we call this? This is going to become methyl propanoate. Methyl propanoate. Is it clear now? Stephen and what's this your name? Medera. Sorry if my pronunciation is not correct. Yeah? Okay, Dera. This your is too trish for Nigerian. Medera. All right, so I think it's clear already. You can go ahead and practice more over time. So that's for your alkyl alkanoate. But let me quickly ask you now. Also in the chat box, this is the same formula You were able to name it. You understand the name. So what is going to be the alkanol and alkanoic acid that we use in the esterification reaction? Which alkanol and alkanoic acid will give us this compound? What's the name of the alkanol and alkanoic acid that will give us this compound? If you know the name, then you should be able to name the alkanol and the alkanoic acid. The alkanol and the alkanoic acid. Oh yeah, quickly. Oh yeah. I'm already spending too much time online. My mommy will beat me. Methanol and propanoic acid. Methanol and propanoic acid. Okay, I think that's correct. Any other person? Methanol and propanol. It cannot be two all now. It will be one all and one oic acid. Enoch. One all, one enoic acid. Okay, methanol and propanoic acid, exactly. All right. So if we split it, of course, this is our alkyl. So this is methyl. So you know it's going to be methanol. And then this one is prop. So that's going to be propanoic acid. I want to believe that you should be able to draw those structures. Now, the final two that we want to talk about, the two functional groups left, we have amines, amines. Okay, amines, we represent them as RNH2. RNH2. All right. So your R, let's say I'm using C2H5NH2. So when I draw that, I'm going to have C2H5NH2. This is how to draw. So you simply count how many carbon atoms? 2 carbon atoms. 8. So this is ethylamine. So we call them alkyl amines. So this is ethyl now. So we're going to call it ethyl amine. Ethyl amine. Sorry about the wrong pronunciation earlier. So you count the number of, you check the alkyl that you add, and then you put amine in front. So if I add methyl, I'll call it methyl amine. If I add propyl, I'll call it propyl amine. If I add decyl, I will call it decyl amine. Okay. So whatever alkyl you add is what gives you amine. So you may want to just, for your practice, what will be the name of this amine here? Kindly use the chat box. C4H9NH2. Very quickly. You're rounding up. C4H9 H2. What's the name of that? I just need one example. Just one answer rather. Oh yeah, people have slept. C4H9NH2. Okay, butyl amine. That's very correct. It's not amide though. Enoch. Amine, Ne, not D. Now the amide is the last one that we want to take for today. So for amide, this is only going to change to D, and there's no alkyl. So amides have a carbonyl bond. So RCONH2. That's for amide. So if we draw it, RC, the double bond, then NH2. So this is for amides, RCONH2. So let's say our R is CH3, then CONH2. So this is going to be CH3, CONH2. So now if I want to name this, for amides, we call them based on the number of carbon that we have in the what do we call it now? In the formula. So for your amides now, I think they are otherwise called alkanamides. Okay, they are otherwise called alkanamides. Okay, so amide or alkanamides. So the alkyne is based on the methyl. So how many carbon atoms do we have here? 2 carbon atoms. So I'm going to call this ethanamide. Ethanamide. Do you get now? Okay, if it was 1 carbon atom, that would be methanamide. Do you get? So because the first one is we have two carbon atoms now. So this is ethan amide. And I think with that, we are going to call it off for tonight. Every other part that you think you have issues with, you can drop it in the group. I would make reference to it. And maybe you're just scrolling to your YouTube and then that's how you found this class. You can also send a message to be a part of our community for the free sessions that we come up with. Okay, you can also check our YouTube channels for other free videos. I think there's a video on solubility product, there's a video on balancing redox reactions, and of course, very soon we'll most likely be having other content on stoichiometry across physics, English, biology, and so on and so forth. But don't forget, most importantly for UTME now, you need to join the Operation Storm UTME classes in order to speed up your preparation. How much can we cover here? This is just organic chemistry, but over there is a laid out structure for you to learn adequately. For those of you that are joined, I'm very much sure that you can testify to how much learning is going on in the platform. For those of you yet to join, of course, feel free to send me a message with the word OSU, and maybe you can describe yourself and tell me you attended the YouTube session. All right. Message on the other end on WhatsApp. Feel free, that is my number, and share our YouTube link with your friends. They can join, and you may not know how much you may help somebody also gain admission. It's a win-win. All right. So we're going to call it off for today. Thank you for joining. If there will be other sessions, of course, on this same channel, I will definitely make proper announcements on the group. Till I see you again, you have a great one. You can shower me love. Many of you are village boys and girls. You don't know how to use most of these, but I will assume you know how to use love. All right, bye. Pẹ̀lẹ́ o.